So we will continue with chapter 21. We will be finishing this chapter today, and we will start recitation on this chapter when we are done with this chapter. So we're going to talk about an alpha-beta unsaturated system before we start talking about some reactions involving an alpha-beta unsaturated system. We are going to talk first about the effects of conjugation in alpha-beta unsaturated aldehydes or ketones. If we look at this compound, you have a keto and you have a double bond between the beta and the gamma. The equilibrium constant to go to another isomer where the double bond is between the alpha and beta is 4.8. This kind of equilibrium is favored because when the double bond is in conjugation with the carbonyl, the isomer is more stable. The smallest alpha-beta unsaturated system is acrolein. You have the C double bond O of an aldehyde in conjugation with the C double bond C, and you can see here the 4p orbitals to be in conjugation. Now, with the alpha-beta unsaturated system, let me put it on the board before I elaborate further. With the alpha-beta unsaturated system, you have two sites of attacks. You don't look at the carbonyl alone. You don't look at the C double bond C alone. We had a similar system with the conjugated diene back in chemistry 211. You remember we had 1,2 addition, 1,4 addition also in a conjugated diene when we were attacking HBr, for instance, and we talk about kinetic control and thermodynamic control back in chemistry 211. There is some similarity right here that you have the reaction to be kinetically controlled or thermodynamically controlled. You have a 1,2 addition and 1,4 addition. You have a conjugated system. You need to look at the conjugated system as a functional group. So here are the two scenarios. I have right here CH2 double bond CH, C double bond OH. We're looking at the smallest alpha-beta unsaturated system, and I am reacting it with a nucleophile. Okay, we will talk about the different nucleophiles later today, but I have the first scenario where I am reacting it with this nucleophile, where this nucleophile is going to attack the carbon of the carbonyl, and I will get O minus, CH2 double bond CH, C double C, now O minus H, and here is my nucleophile. Whether you drop H2O plus, so this is number 1, or water, depending on the nucleophile, let's say H2O plus, we are getting here CH2 double bond CH, CH, O, H, and here is the nucleophile. Okay? We refer to this as a 1,2 addition. I have 4 atoms as my functional group. I added at the 1 and 2, that doesn't matter from where you are numbering, it's just the number 1 to 4. Here we are talking about having 4 atoms in our functional group. We call it 1,2 addition. But there is another possibility, which is the following. This CH2 double bond CH, C double bond O, H, and I am reacting it with my nucleophile. this nucleophile can attack the beta carbon. As such, the double bond will go over here, and this will go over there. So what will be my product, or intermediate in this case? Here is my nucleophile. I have CH right here, double bond C, O minus, hydrogen. So my nucleophile now attack the beta carbon, not the carbon of the carbonyl. Then in number 2, when I am adding H3O plus, I am gonna get the enol, which will tautomerize into the ketone. Well, the keto here is an aldehyde, so will tautomerize into the carbonyl H. Now, the nucleophile is added at number 1 and the H at number 4. Okay? We refer to this as the 1,4 addition. So the 1,2 addition, you are attacking the carbon of the carbonyl. The 1,4 addition, you are attacking the beta carbon of your alpha beta unsaturated system. Now we are going to figure out which nucleophiles will do 1,2 addition, which nucleophiles will do 1,4 addition. Now the 1,2 addition is our kinetic product. It is a faster one. This is kinetic. The 1,4 addition is the thermodynamic. It is more stable because a carbonyl is more stable than C double bond C. Clear what is the 1,2 addition, 1,4 addition in an alpha beta unsaturated system? So what we are going to figure out later, that if I have a lithium aluminum hydride, I will do 1,2 addition. I'll be reducing the carbonyl. You reacted with sodium borohydride, you will do 1,2 addition. You reduce the carbonyl. You react with an alkynylide or acetylide, RC triple bond C minus or HC triple bond C minus. So these are strongly basic. Okay, you will have 1,2 addition. Why? If you use a weakly basic nucleophile, so the good nucleophiles that we circled back into 11, cyanide, thiolate, azide, all of these, they are going to do 1,4 addition. Then it gets more interesting as we cover this part. We take the enolate of an alpha beta of beta diketone, of beta ketoester, beta diester. Since the enolate of all of these are weakly basic, they will do 1,4 addition on an alpha beta unsaturated system. Okay, so what we are going to discuss from now till the end of this chapter right now is the 1,2 addition versus 1,4 addition, what kind of nucleophile we are using, and then what happens next. And it's going to get very, very interesting. So let me share the PowerPoint. Again. And we discuss again the 1,2 addition and 1,4 addition. Now, why are we having the possibility of a 1,2 addition or 1,4 addition? If you look at the resonance picture of an alpha beta unsaturated system, well, if you move the double bond over here, you see that you have a delta plus on the carbon. So this is the possible site of a nucleophilic attack. When I have nucleophile, I can attack the carbon of the carbonyl because I have a partial positive charge on that carbon. If you delocalize the double bond over here to get this resonance structure, you see that you have a delta plus on the beta carbon. So this nucleophile has a choice to attack either the carbon of the carbonyl or the beta carbon of your alpha beta unsaturated system. So two sites of attack, beta carbon or carbon of the carbonyl. Dipole moments. If you look at butanal versus trans 2-butanal, here the dipole moment is 2.7 d-bonds, while in the trans 2-butanal, you have the compound to be much more polar. So you have a greater separation of charges since you have the dipole moment to be large. So let's talk about the conjugate addition to an alpha beta unsaturated system. The 1,2 addition, that will be a direct attack. The nucleophile will attack the carbon of the carbonyl. The 1,4 addition, we also refer to it as the conjugate addition. Your nucleophile will be attacking the beta carbon. Kinetic versus thermodynamic control. The nucleophiles that attack the carbon of the carbonyl, so that will be leading to the kinetic product or products if you have more than one. And the attack at the beta carbon will result into the thermodynamic product because the carbonyl is more stable than the alkene. So 1,2 addition versus 1,4 addition. A 1,2 addition with an HY or Y minus first and then H2O plus second. You have the Y to attack the carbon of the carbonyl and the oxygen will be protonated. That will be formed faster, and that will be your major product under the kinetic conditions. And that will lead whenever your addition is not reversible. A 1,4 addition, you will have the Y to attack the beta carbon. You are going to get the enol. The enol will tautomerize into the keto form, so you will get the carbonyl. And that is referred to as a 1,4 product. You will isolate the 1,4 product. You will not isolate the 1,2 product. It is more stable than the 1,2. Why it is more stable? Because the carbonyl is more stable than an alkene bond. So what are the nucleophiles that undergo 1,2 addition? Grignard reagents, lithium aluminum hydride, sodium borohydride, and an alkenylide. Strongly basic nucleophiles, they add irreversibly. For instance, I have this alpha beta unsaturated system. I have acetylate first in THF, then HCl plus. Remember, first THF, because you don't want to quench your Grignard. So C minus is attacking the carbon, you get O minus. Because it is an acetylate, you have 1,2 addition. So you have to identify first what is your nucleophile. Is it doing 1,2 addition or 1,4 addition? And then you put the product. So that will be your product. 1,4 addition, the weakly basic nucleophiles, the excellent nucleophiles that are weakly basic, cyanide, thiolate, ammonia, amines, azide, they all do 1,4 addition. Weakly basic nucleophiles, they add reversibly. So whenever you are having an alpha beta unsaturated system, and you know it is 1,4 addition, the 1,2 addition, it's very straightforward. You can write it right away. With the 1,4 addition, please make sure you do the mechanism as I did here. Draw the enolate, protonate it, and then do tautomerism so that you don't miss the structure, the final structure, and you do not write the wrong structure. So what do we do here? I have the Cn minus attacking here. This will come here. This will go over there. This is how I did it over here. So I got the enolate. You protonate it from ethanol in this case, or acetic acid. Then you have the enol, then tautomerize. Okay? Here is another example. I have an alpha beta unsaturated ketone, and I am reacting it with benzyl thiol in the presence of hydroxide ion. So first, the hydroxide ion is going to react with the thiol acid-base reaction so that I will get the thiolate. I have RS minus here. RS minus will undergo 1,4 addition. So the RS minus will attack here. This will go here. You get O minus. This is, notice I will always draw the more stable resonance structure like I did on the board earlier. So I got this enolate. I protonate. I got the enol, and then I tautomerize. That is the problem. So now that we know what is a 1,2 addition, what is a 1,4 addition, let's take it a step further. If I generate an enolate of a beta keto system, beta diketone, beta ketoester, beta diester, beta cyano, carbonyl compound, beta nitro, carbonyl compound, I will be able to get an enolate. And that enolate is weakly basic. It will undergo a 1,4 addition on an alpha beta unsaturated system. This is called the Michael addition. Okay? So if I have ethyl acetoacetate and I react with sodium ethoxide, now I have the enolate of ethyl acetoacetate. If I have a beta keto, well, here diethyl malonate, and I react with sodium ethoxide, I am able to get the enolate of the beta of my diethyl malonate. And if I react with an alpha beta unsaturated system, I will be getting 1,4 addition. It will be Michael addition. So for instance, let's look over this. I am gonna work on the board repeatedly, so I will stop sharing and then share again because I want to go over the mechanism. So let me first draw on the board what kind of reaction based on this I am gonna do. So I have O ethyl, C double bond O, CH2, C double bond O, O ethyl. I'm reacting it first with NaO ethyl in ethanol. Second, I am gonna react it with this alpha beta unsaturated ketone. Okay. Third, I am gonna add H3O plus. Fourth, I am gonna add NaOH water. 5, I'm gonna add heat. Okay. So let's see what we're gonna get with this. So first, I took my diethyl malonate and I reacted it with an alpha beta unsaturated system. Well, first with sodium ethoxide. So my first step is the following. C double bond O, O ethyl, C H H, it's an acid-base reaction. O ethyl, because we talked about this hydrogen, it is acidic, pKa in the order of 13. So when I am reacting it with the sodium ethoxide, so we're doing step number 1 now in ethanol. I am having an acid-base reaction. So what did I generate? I generated, I'm gonna draw it in this way. Space here. So I generated right here CH minus C double bond O, O ethyl, C double bond O, O ethyl. This is the enolate of my diethyl malonate. In step 2, I reacted it with an alpha beta unsaturated system. The enolate of diethyl malonate is a weakly basic nucleophile. When I am reacting it with an alpha beta unsaturated system, it will do 1,4 addition. So this will attack right here. This will come right here. And this will go over there. Okay, so what did I generate? CH2. Attach CH, C double bond O, O ethyl. C double bond O, O ethyl. And then here I have CH double bond C, O minus, CH3. Any questions till now? Clear? Okay. Now, guys online, feel free to jump in and ask any questions. In number 3 right now, I added H2O plus. So I am going to form the enol, and then what's next? Tautomerism. Okay? So it is going to be CH, C double bond O, O. CH double bond C, OH, CH3, which will tautomerize into the keto. So I got C double bond O, CH3, CH2, CH, C double bond O, O ethyl, C double bond O, O ethyl. Now here in step 3, you can monitor the pH. It could be just adding water will do it, okay? So now, number 4, I added an AOH, water. So what am I going to do now? Saponification. I have 2 ester groups. The 2 ester groups are going to be saponified. I skipped right here. Let me put H3O plus and heat, or 5 H2O plus and 6 heat. You can see where I am going with that. So I am going to get CH2, C double bond O, CH3, CH, C double bond O, O minus, C double bond O, O minus. Now you are adding H2O plus. We draw first whether you put H2O plus comma heat 5 or 5 H2O plus and 6 heat. Always draw the intermediate, and then you are going to do the decarboxylation. So what are we going to get now? C, let me use a different color so that you can see it because it's getting crowded here. C double bond O, CH3, CH2, CH, C double bond O, OH, C double bond O, OH. Now with heat, again, whether it is condition number 6 or H2O plus comma heat, you are going to get rid of a CO2 that has a carbonyl beta to it. So basically, you can get rid of one of these 2 CO2s, not both of them, because this carbonyl is not beta. This carbonyl is beta to the CO2, and this carbonyl is beta to the CO2. So you're getting rid of one carbonyl. Doesn't matter which one right here. Your final product is going to be CH3, C double bond O, CH2, CH2, C double bond O, OH. This is your final product of this reaction. Did I miss one carbon? I could. Well, let's follow up. Where did I miss? So let me see. Here, we're fine. CH minus. We're fine till here, right? You guys can see better than me. Right here, I skipped one CH2, yeah? Okay. So let's add it everywhere. Right here, we have a CH2, CH2, while we are waiting for electricity to be back. Okay? So in this reaction, we had the enolate of a diethyl malonate. It could have been the enolate of beta-diketone. It could have been an enolate of beta-ketoester, beta-cyano, etc. As long as you are having that hydrogen to be at the alpha to be acidic. Okay, so I added the CH2s, and that will be our final product. So we got the enolate, we did 1,4 addition, and then we took it further. Because I have a diester, I can do saponification, and then I can do decarboxylation. Any question? People online, do you have any questions? Okay. So let's go over it on the PowerPoint. With KOH ethanol, they are using right here, we are having the alpha beta unsaturated system to react with the enolate. The enolate will do the 1,4 attack. That will be the product. Then, if you are going to do the saponification, then protonation, and then heat, you're going to get this product. What I did, I actually worked out the mechanism. I changed a little bit the conditions, but I worked the mechanism of this entire reaction. Now, here is another example. I have now beta-diketone, right? This is a beta-diketone. I am reacting it with an alpha-beta unsaturated system in the presence of KOH and methanol. So I generated the enolate and I attacked right here. Now this is going to get much more interesting. Why is that? Okay, so we already know the mechanism how to get here. I just did this mechanism, right? But then this can go further because you can do an intramolecular aldol condensation by deprotonating the hydrogen right here and attacking one of the carbonyls. And that will lead to a 6-membered ring, and that will be called Robinson annulation. A Robinson annulation is a Michael addition followed by an intramolecular aldol condensation. How so? If you remove this hydrogen, so you have the enolate right here, you attack this carbon, what is the ring size? 1, 2, 3, 4, 5, 6. An intramolecular aldol condensation will get you a 6-membered ring, and then you can also eliminate to get the C double bond C in conjugation with the carbonyl. So Robinson annulation, it's a Michael addition followed by an intramolecular aldol condensation. This will happen when you are able to get a 6-membered ring. So we just talked about this right now. Okay, if you take this product and you react it with potassium hydroxide and heat, this is going to be your final product. How so? Well, KOH is getting you this enolate. So you got the minus right here attacking this carbon O minus, and then O minus will be protonated from water. So you got this OH. You will always have elimination so that the C double bond C is in conjugation with the carbonyl. Even at room temperature, this elimination will happen. You eliminate right here, and then you got the C double bond C to be in conjugation with the carbonyl. I'm going to do an exercise right now when I am done with the remaining 2 slides, where I want to have the final product, this one, and I want to go backwards to find out what is my diketone and what is my alpha beta unsaturated system. There will be 2 or 3 exercises like this in the clicker session that we will do before the final exam, and you need to figure out what are the starting materials. So we are going to do this exercise at least 3 more times when we do the clicker sessions in the last 2 sessions before the end of the semester. So this will not be isolated. You are going to get the C double bond C in conjugation with the carbonyl. Our final reaction is the organocopper reaction with an alpha beta unsaturated system. It will do 1,4 addition. This is because of the size of an organolithium reagent of the dialkyl lithium cuprate, sorry. Because it is too big, it will undergo 1,4 addition. So what I want to do right now, I want to take this and I want to do a retrosynthesis. This is the end of this chapter, but I want to draw the structure before I stop sharing. And I want to do the retrosynthesis. So the question is the following. We have our final product to be this one. Double bond O, CH3, double bond C right here. And here, double bond O. Yeah? So I want to do this retrosynthesis to figure out how, in fact, this one is coming from this plus this one. Okay? So I am going to go right now backwards and figure it out. So retrosynthetically, we know that the alkene comes from the alcohol. Okay, the elimination is happening so that you are getting the C double bond C in conjugation with the carbonyl. That is coming from the alcohol. So this is coming from this. Okay, are we fine till now? Okay. Now, how am I getting the OH? It must be getting from an enolate attacking the carbonyl. So I must be breaking right here. Okay? So this is coming from this. Double bond O, double bond O. I have the CH3. This is the CH2 minus right here. Isn't it? Isn't this enolate effectively That minus is attacking the carbon of the carbonyl so that I get the OH. So this enolate is coming from this one. Okay. Clear till now? This is the intramolecular aldol condensation. Now you can number your carbons, 1, 2, 3, 4. Now, how am I gonna link this to that? I must be having the enolate at this carbon attacking this carbon. How can I get the carbon that is beta? I must have an alpha beta unsaturated system. So retrosynthetically, this comes from this one, CH3 minus, that's my enolate, attacking what? The C double bond C is between carbons 1 and 2, and carbon number 3 is my carbonyl, and I have a methyl group right here, which is carbon number 4. So what is this one? Here it is. These are my two starting materials, the diketone and the alpha beta unsaturated system. We did it retrosynthetically right now. Now this question could be asked, and then you can have 9 different choices, combinations. I can come up with different diketones, different alpha beta unsaturated systems. I can, and then I will be matching them. This one and this one, this one. How can you find it? You do this. As I did retrosynthesis, we're gonna do it again in the 2 problem-solving sessions before the end of the semester. Any questions? People online, do you have any questions? Anybody? Do you have any questions? Okay. So with that, we are going to start recitations. On this chapter, I am going to continue the remaining half an hour or so today, recitation. And next week, Tuesday, definitely it's going to be a hybrid session. So I will be solving. Depending how much I am solving on Tuesday, I will see whether Thursday is going to be hybrid or it will be completely online, because the number of people who are showing up right here is very small. So I prefer to do everything in SLH. How many do we have here? 4, 5, 16, 17. So it's only the first hybrid session that we had the maximum number 22. Now we have only 17 of you right here. Anyway, so, but Tuesday session is definitely hybrid. And on Tuesday, I will decide what to do about Thursday. So let's start with some reactions. From your book, 21.40. Okay. Reacting it with CH3, CH2, 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 Br in the presence of Na or ethyl ethanol. Then in part B, you're reacting first with sodium hydroxide, second H2O plus. You see the pattern. It's going to be always. You do a reaction, then you do saponification, protonation, decarboxylation. So what is happening in, this is part A, and this is part B. So these are 2 reactions from the 2140. So this is part A, and this is part B. But usually, we always put them together, like I did earlier today. So you have 1 sodium ethoxide, second the alkyl bromide, third sodium hydroxide, fourth HCO plus, fifth heat. Or HCO plus, comma, heat. You draw the product, then you do decarboxylation if there is decarboxylation. So what are we doing first? The sodium ethoxide is giving you the enolate of your beta keto ester. And then what are you doing? An acetyl reaction. Whether you are having a methyl or primary or secondary, the enolate of beta diester, of beta diketone, of beta keto ester will give you an acetyl reaction with the alkyl halide, as long as it's not tertiary. So basically, this is attacking right here. I'm going to show you some arrows as I am covering reactions as well, just to remind you of the reactions. So what are we getting? Our product right here, C double bond O, CH3, C double bond O, O ethyl, and then I have CH2, 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 CH3. I did the acetyl reaction. What's going to happen next? Saponification. So this is going to be OH, O minus first, then OH, then you're getting rid of all of this. So what is your final product? CH3, C double bond O, CH2, 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 CH2. Count the number of methylene. In the choices, there will be one missing, methylene. Okay? So, what is our final product? CH3, C double bond O. I have here 1, 2, 3, 4, 5. It's going to be, this is 1, 2, 3, 4 methylene, and this is my methyl group. Any questions? People online, do you have any questions? Students online.
Can you repeat part B, please?
Part B, okay. So sodium hydroxide, what does it do? Saponification. So you get O minus. So in first, you are getting CH3, C double bond O. Here, CH, CH2, 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 CH3, C double bond O, O minus. Then you added HCO plus. O minus will be OH. Then you added heat. This carbonyl is beta to the CO2. I told you this is going to be repeated almost in all reactions. You get rid of the CO2. Okay? So your final product will be CH3. This hydrogen is going to be here now, CH2. And then we have 3 methylene groups and CH3. Can I erase? Okay. So I will go to the next one. I'll leave this for a second in case some people are still copying. Part C. You have acetophenone, and you are reacting it with diethyl carbonate in the presence first of sodium ethoxide, second HCO plus. So I'm going to erase now. Anybody is still copying? Okay. What are we doing here? Excuse me. What are we doing? Well, no. Because an AO ethyl with ethoxide, you are having the same thing. So nothing will happen. The reaction is not productive. We have a mixed Claisen condensation. One of our reaction cannot generate enolate. The diethyl carbonate cannot generate enolate. The ketone, if you form an enolate, you are not going to get an aldol condensation. Why not? why the enolate of acetophenone is not going to react with acetophenone. Because the direction of equilibrium to form the aldol condensation is not favored in ketones unless it is an intramolecular aldol condensation. So your only option is that the enolate of the ketone is attacking the carbonyl of the diethyl carbonate. Okay, so if we are doing this as a MCQ question, or if I want just show me the product of this reaction, so what do you have? CH2 minus, right here, is attacking here. You get O minus will come back and will kick this out. Then you have an acid-base reaction, then you are protonating it. So you see, now I am showing you how to draw the final product right away without, I showed you earlier the step-by-step mechanism. Now I am going to show you, if you are asked, what is the product of this reaction? How do you do it very fast? Okay? So I am getting the enolate of my ketone, and that enolate is attacking my carbonyl. So what is my final product? C6H5, the phenyl, C double bond O, and now I have CH2, C double bond O, O ethyl. Now, why I am adding H2 plus? Because I am having the acidic hydrogen, the second acidic hydrogen right here to do an acid-base reaction. I added H2 plus to protonate it. Remember the mechanism of the Claisen condensation? Part D is similar to part C. Let's do parts E and F. We fine? Any questions about this? And about part C? Anybody has any questions about part C? Okay, I'm going to erase it, and we are going to do now parts E and F. They are related. Yani the products of E is subjected to the conditions in F. So part E, I have diethyl malonate. You are reacting it with this alkyl halide in the presence of NaO ethoxide, sodium ethoxide, ethanol. You are getting a product. That product is subjected in part F to first an NaOH, water, second H2 plus, third heat. So what's happening first? Enolate to do what? A Santo reaction. Yeah, I'm getting an enolate. You see repetition. It's going to be, the same question will be in the final exam. It's all you are having a different enolate, different alkyl halide, and then the condition sodium hydroxide, and then water, and then HU plus, and then heat will definitely be there in like probably 5 to 10 questions in the final exam. Okay, it's a regular thing. Okay, so I am getting the enolate. I am going to be attacking this carbon. Number your carbons so that you don't make any mistake. 1, 2, 3, 4. Now, if I have any chiral center at carbon number 2, this chiral center is not affected. But if I have a chiral center at carbon number 1, what's going to happen? Inversion, because I'm doing an SN2. But SN2 happens only at the carbon that is attached to the leaving group. Okay, let me make sure that I drew the structure correctly of the alkyl halide 1, 2. At 2, I have a methyl, 3, 4. Okay. So what am I getting right here? I am having CH, C double bond OO ethyl, C double bond OO ethyl. Always draw it like this. It's easier to see the final product right away, because you're putting them beta to each other, you know you need to decarboxylate when you draw it as such. You're drawing it like Y. Yeah? Draw it like this. It's so helpful for you to see what you are going to draw as a final product. And also it is helpful as you are putting the alkyl group not to miss any methylene like I did earlier. I didn't see it when you saw it. But when you are drawing it, you won't make a mistake. Okay? So now this CH right here, you see now I am showing you the faster way. At the beginning, I did the step-by-step mechanism. Now, this CH is now gonna be bonded to CH2 number 1. This is carbon number 1, which is attached to CH3, CH2, CH3. This is 2, this is 3, this is 4. Now, I didn't put R in the question. There was no R and S at carbon number 2, so that's why we don't worry about it. Now, can you see how to draw the final product right away without going through the intermediate? Because what's going to happen, you are going to get O minus, O minus, OH, OH, and you get rid of one of them. Clear? Yeah? So what is our final product? In part F, I am having now CH2, CO2H. And then here, this is the CH2 number 1, CH, CH3, CH2, CH3. Now on my scratch, I'm drawing it like this so that it is easier for me not to miss any methylene group, not to add groups or remove any groups. So that will be my final product. Fix the CO2H. So you draw it then the correct way. CH2, CO2H, the carboxylic, CH2, CH, CH3, CH2, CH3. Yeah? Any questions? People online, do you have any questions? We're fine. So this is the same, right? I'm just drawing the structure in the right way. Yeah. Any question? Are you seeing the fun of this chapter or not yet? Okay. Okay, I'll erase this and we go to the next part. This one, I want to do the mechanism. Okay, so this is part I. You have this ketone, actually ester, sorry. You're reacting it first with LDA, second with C6H5, C double bond OH, C double bond OH aldehyde. Third, they are giving you only H3O plus. Here, we will keep it as is, and then I can modify the question. What happens? I want to do mechanism, not just the final product. What happens when you take an ester and you react it with an LDA? What is LDA? What is LDA? It's a strong bulky base, lithium diisopropyl amide, right? So this is LDA. LDA will generate the enolate of an ester quantitatively, or of a ketone quantitatively, or of an aldehyde. This LDA will take this hydrogen, and I am going to form the enolate of my ester. So what am I getting? C double bond C, O minus, O tertiary beta. Clear till now? Now, in number 2, I dropped my aldehyde. So I am doing a mixed condensation, mixed Claisen condensation, basically. You form the enolate of the ester, and then you added the aldehyde. So in number 2, you added C6H5C double bond OH. The enolate is going to attack the aldehyde, the carbon of the carbonyl. So what are you getting? C double bond O, O. Right here. Then CH2, CHO minus, C6H5. Yeah? You protonated. What's going to happen? Number 3. You're going to get C6H5, CHOH, CH2, C double bond O, O, tertiary beta. Yeah? So you have a mixed Claisen condensation. The LDA is getting you the enolate quantitatively of the ester, and then you drop the aldehyde. Now, you could heat this in number 4, then you will get the C double bond C to be in conjugation with the carbonyl and the benzene. Okay? So then you can get C6H5, CH, double bond CH, C double bond O, O, tertiary. Any questions? Online, anybody has any questions? Okay, let's go to the next 2 parts also. We're gonna do both of them, G and H, or whatever. We're going backwards now. Here it is. I have now this alpha beta unsaturated ketone. And I am reacting it with diethyl malonate. In the presence of sodium ethoxide, ethanol. This is part G. In part H, you are reacting with H2O, HCl, and heat. So, what am I having here? The enolate, and then 1,4 addition. This is a Michael addition. Okay, so I am going to do it the faster way. The faster way, meaning, let's say you are asking an exam, what is the product of this reaction? You have the alpha beta unsaturated ketone, first an AO ethyl, second, I will have diethyl malonate. First, to the diethyl malonate, I'm adding sodium ethoxide. Second, the alpha beta unsaturated ketone. Third, H2O, HCl heat. What's the product of the reaction? How do you do that in the final exam as an MCQ? How do you do it? Well, right here, I have the minus to attack here, this will go there. You draw the intermediate. Okay, so what is my intermediate? This here, O minus, which will be OH. Now you can do it right away. This is here, I have CH, CO, C double bond O, O ethyl, C double bond O, O ethyl. Now, right here, what is my product? Tautomerism. Okay, so my product will be this one. Double bond O here, and then I have CH, C double bond O, O ethyl, C double bond O, O ethyl. Oops. Yeah? Now, we're doing it differently. We're not doing saponification, then protonation, then heat. We are doing decarboxylation under acidic conditions. So you are getting the dicarboxylic, and then you're deprotonating. So you are forming first right here, this one. Then what are you doing? Decarboxylation, you're getting rid of one CO2. Your final product will be this one. Trust me, if this question were to be in the final exam, one of the choices will definitely be where there is a double bond right here, and that will be the wrong answer. That's why you have to draw this. Definitely one of the wrong choices will be this, exactly the same. Everything is the same. I'm just putting a double bond right here. That will be the wrong answer. Any questions? People online, do you have any questions?
Professor, can G undergo Robinson and form a cyclic, a six-member ring, or no?
No, why not? Why this one can never undergo Robinson? There are many reasons why it cannot do Robinson. First, you cannot generate enolate of this carboxylic acid. You're talking about the final product, right?
Yes.
Eddie?
Yeah.
First, you can generate enolate of a carboxylic acid. So if this were to be a methyl, can it undergo a Robinson annulation? And the answer is no, because you need to get a fused system. You will not get a bridge system. We're gonna do examples of Robinson annulation in the next exercise. Well, in the next recitation. There are so many good questions in your book, and we're gonna try to solve many of them in the next recitation. So I'm gonna stop right here for today. I will see you in the exam on Saturday, and best of luck.
Thank you, Professor.
Thank you, Professor. Have a nice day.
You most welcome.